Just to recap, we said we have this unofficial definition of energy, and we can think of this in one of a number of ways. We can say more energy increases the likelihood of some system, so it can be to chemicals or some mechanical system, so of some system to change its state or to affect its environment in some measurable way. Right, so this was our kind of unofficial definition of energy. It's got to do with allowing things to change their state. It can be a temperature change of color, a change of volume, change in speed, change in form. All of these things are measurable changes and is somehow linked up to energy. The more energy the system has got, the more likely it is to undergo some sort of change or to affect its environment in some way. And then we looked at specifically mechanical systems. So specifically mechanical systems with non-deformable, unbreakable, objects. So these are the things we've been looking at so far, things on which forces act. So we said, okay, if this is kind of a guide to what energy is all about, if we look at non-deformable, unbreakable objects, so if I've got some block over here, and if there's a force applied, and this block is displaced by a certain distance, then we said that, well, the greater the distance over which this force is applied, the larger the velocity of this block will be in the end. The larger its velocity is, the more it can affect something with which it collides. So somehow, if we think about our definition of energy, this force acts to transfer energy to the block, because the longer this force acts, or the greater the displacement over which this force acts, the faster and faster the block will move, which means the more and more it can affect something it collides with. And we defined this transfer of energy, we called this work, and we could put a number to that. We said, well, the work is equals to the force vector with dot product or scalar product with the displacement vector. Right, that's simply how we define work. This is if the force is constant. Now we can do a quick example just to make this a bit more understandable. So, an example. So what is the easiest in the following two, from the following two scenarios? You've got a couch. So this is an artist's impression of a couch, I guess. So there's a couch, and this couch needs to be moved 2 meters over a carpeted floor. And you've got now an option. You can push down on this couch with a force, say, equals to 40 Newton. And let's say this force makes an angle of 30 degrees. with the horizontal. Or the second option is you can pull the couch again with a force of 40 Newton over the carpet. And in both cases, no matter what you do, you get that the speed of the couch remains constant. So, which one would be the easiest to do? Which one would make you least tired after the couch has moved? No, sorry? Answers? The pulling. Can anyone tell me why they would choose pulling rather than pushing? Yes?
Because so the friction is equal to the coefficient of friction times the normal force, so when you push down, there is an increased force.
Yes, so what she said is, in this case, if we draw a free body diagram of the couch, we've got its weight, mg, we've got our force that acts downwards, so we've got our applied force that has an x component, and our applied force has got some y component, and we've got a normal force that has to oppose both of these. So our normal force will be equals to the magnitude of the y component of the force that we're applying plus mg. And we said the coefficient of friction is related to the normal force through this. So pushing down means you're increasing the normal force, you're increasing friction. Friction will act in that direction on the couch. So you basically increase the force of friction. Now another thing to think about here is, given that the couch, that it moves at a constant speed, what would be the total amount of work done be on the couch? 0. Why would you say 0? So acceleration is 0, so the only thing we can say is, well, this couch is moving at a certain speed. If it increases, yes. That's a good.
So the kinetic energy is 0 since F final is equal to F.
Okay, that's it. You anticipate a result that we're going to do a bit later on, linking work and kinetic energy. But you can argue this from two ways. You can say, well, if the velocity is constant, there's nothing, this couch doesn't gain velocity. So overall, it's not gaining energy. Alternatively, you can say, well, constant velocity means the resultant force acting on the couch is 0. If a resultant force is magnitude 0, it cannot do work, because work is some force dot a displacement. So if the total force is 0, the total work done will be 0. So in both cases, the resultant force is equals to 0. Therefore, the total work done on the couch will be equals to 0. But this does not mean you're not doing work, right? It means you are doing some work, but the same amount of negative work is done by friction. So you're trying to impart motion to the couch, and friction is almost trying to, for every little bit of energy you transfer, friction saps it away, and the two balance out exactly. So if we were to put numbers to this, let's say the couch has got a mass equals to 5 kilograms. Then we can calculate the amount of work done over here by us. So remember, we said it's only the component of the force that's in the direction of motion that actually does the work. The rest of it is almost wasted. In this case, that's not entirely true. The y component increases friction, which actually increases the force opposing. So the amount of work that you do is equals to this force vector that we're applying dot the displacement vector. This is just equals to the magnitude of the force that you're applying. It's 40 Newton. The magnitude of the displacement is 2 meters times the cosine of the angle between them, which in this case would be 30 degrees. and this is 0.8. Someone can quickly just calculate this number for me. Sorry? Okay, well, while you calculate that, we can look at this example. Sorry? 69,28. Right, so, and the work done against friction. So this is the, you can go and calculate it for yourself. Okay, so the important thing here to emphasize is, remember friction, because if you increase the normal force, you increase friction, so the amount of work you have to do to oppose friction now becomes more to keep this thing going. In the second case, because you're pulling, you actually reduce the normal force, so you reduce friction, so the amount of work that you do is less. Again, this problem is actually, this example is slightly overspecified. If you just know the mass of the couch, you can actually figure out what the magnitude of the forces that you will be applying. But the idea of this was just to show you with numbers how you can calculate the work done.